Let's verify that this equation is an identity. I notice that I have fractions on the left-hand side, which to me means I want to find a common denominator. I'm going to multiply the left-hand fraction by 1 plus sine of x, and I'm going to multiply the right-hand fraction by 1 minus sine of x. Remember when we had sort of instructions as to how to verify identities and work through things, you wanted to typically work with one side rather than both sides, and you want to work with the more complicated side, with the right-hand side being your goal, or the easier side being your goal. So the left-hand side looked more complicated to me because I needed to, I can find a common denominator. I think it would be more difficult to split up the tangent and secant and turn it into a fraction than it would be to work with the left side to get to the right side. Multiplying, I get 1 plus sine of x minus 1 minus sine of x over 1 plus sine of x times 1 minus sine of x. And that's going to be equal to 2 tangent x secant x. Okay. I'm going to distribute. That's going to give me a -1 and a positive sine x. In the denominator, I can expand or FOIL that out. So in the numerator, I'm going to have 1 minus 1 and sine x plus sine x over, first is 1 times 1, outer is minus sine x, inner is plus sine x, and last is minus sine squared x. And that's equal to 2 tangent x secant x. In the numerator, I wind up having 2 sine x's. In the denominator, the sine x terms cancel, and I just have 1 minus sine squared x. That's equal to 2 tangent x secant x. And thinking about the right-hand side, tangent is sine over cosine, and secant is 1 over cosine. And I look at the left-hand side, I don't have any cosines, but I can get there. Let's remember that Pythagorean identity that the sine squared of x plus the cosine squared of x is equal to 1. If I manipulate this by subtracting sine squared of x on both sides, then I have that the cosine squared of x is equal to 1 minus sine squared of x, which I have in the denominator. So I'm going to replace the denominator by cosine squared of x. I then have 2 sine of x over cosine squared of x equals 2 tangent x secant x. Tangent is sine over cosine, and secant is 1 over cosine. So I really need the cosines split up. So let's say I have 2 sine of x over cosine of x times 1 over cosine of x equals 2 tangent of x secant of x. And there I have it, because sine of x over cosine of x is tangent of x, and 1 over cosine of x is secant of x. And the left hand now matches the right hand. Okay, verifying that this is an identity, I have a fraction, which I need to get just a cosine. I need to find a common denominator then, which means I'm going to multiply that 1 by 1 plus the cosine of t over 1 plus cosine of t. That's going to give me 1 plus the cosine of t minus sine squared of t all over 1 plus the cosine of t equals cosine of t. Now, I want things in terms of cosine instead of sine. So let's use what we did previously, that the sine squared of t plus the cosine squared of t is equal to 1 to get sine squared in terms of cosine squared. So sine squared of t is equal to 1 minus cosine squared of t. Let's replace sine squared of t then with 1 minus cosine squared of t, because our end goal helps guide us to say we don't want sine in this equation. Minus the statement 1 minus cosine squared t all over 1 plus cosine t equals cosine t. I need to distribute that negative. That becomes 1 plus cosine t minus 1 plus cosine squared t all over 1 plus cosine t equals cosine t. That leaves me with cosine t plus cosine squared t over 1 plus cosine t equal to cosine t. I recognize that the numerator shares a cosine t. I can then factor that out, which leaves me with cosine t times 1 plus cosine t, which looks familiar and helps me know that I am headed in the right direction. The 1 plus cosine t's cancel, and so I then have the cosine of t is equal to the cosine of t, which verifies that identity. We are going to verify that this equation is an identity involving natural logs and absolute values. So we need to know some natural log properties and some absolute value properties. Let's establish a few here. The absolute value of a product is equal to the absolute values of each item multiplied together. So the product of A times B inside the absolute value is the same thing as the absolute value of A times the absolute value of B. And in terms of natural logs, or logarithms in general, addition can be condensed into multiplication, subtraction being condensed into division. The natural log of A plus the natural log of B is the same thing as the natural log of A times B. The natural log of A minus the natural log of B is the same thing as the natural log of A over B. And the natural log of A to the B power is the same thing as B times the natural log of A. Those are the common logarithm laws, and they are, remember, logarithms are inverses of exponentials, and that's where those laws come from. What I'm going to do then is I am going to rewrite, first of all, cotangent in terms of sine and cosine, because my end game goal on the right-hand side is cosine only. That means I'm going to have the natural log of the cosine of x over the sine of x, absolute value, plus the natural log sine of x, absolute value, equal to the natural log cosine of x and absolute value. I can then condense the cosine of x, sine of x, absolute value with sine of x. I'm going to multiply those. And because they are in the absolute value, first I'll write it like this for you. The cosine of x over sine of x, absolute value, times the absolute value of sine of x. That's equal to the natural log of absolute value of cosine of x. And then I can combine these two into the same absolute value based on the rule that I put up here. That's going to give you cosine of x, sine of x, over sine of x in absolute value. That's equal to the natural log of cosine of x. And notice that those sines of x cancel, and you have the natural log absolute value of cosine of x equal to the natural log absolute value of cosine of x, which verifies the identity. We are going to verify this identity by manipulating each side of the equation independently. The first thing that I want to do is multiply the left-hand side by 1 plus cosine of x over 1 plus cosine of x. That's the sum and difference formula in the numerator. That's going to become 1 minus the cosine squared of x, which is the same thing as sine squared of x, over cosine x times 1 plus cosine x. And I'm not going to simplify that just yet. The right-hand side, I'm going to rewrite tangent as sine over cosine. So that's going to be sine of x times sine of x over cosine of x times 1 plus cosine of x. I'm going to take 1 minus cosine of x squared and call that sine squared of x, all over cosine x, 1 plus cosine x. Sine times sine is sine squared x, all over cosine x times 1 plus cosine x. And that verifies this identity. I think it would be really hard to go from just one side to the other in this case. I recognize you could cross multiply if you wanted to verify this identity. That would be another way to verify this by manipulating the equation, but it said manipulate each side independently, and so I wasn't cross multiplying because then that actually manipulates both of them together. And lastly, we are going to be writing this expression x squared minus 121 as a function of theta, where theta is between 0 and pi over 2. using the substitution that x is equal to 11 secant of theta. That's 11 secant of theta squared minus 121, which is the same thing as 121 secant squared of theta minus 121. Now notice that 121 is common to both terms, so I can write that as 121 factored out, and that's secant squared theta minus 1. Using square root properties, I can take that as the square root of 121 times the square root of secant squared theta minus 1. The square root of 121 is 11, and we're talking about theta in between 0 and pi over 2, where both x and y are positive. So I'm just going to have a positive value, not a negative value when I'm square rooting. And secant squared theta minus 1 is the same thing as tangent squared theta, which I can then square root to become tangent of theta. That is 11 tangent of theta. And that's it for this section.